Okay, we are in chapter 7. This is basically, seems like a repeat of a lot of things that we have done, but they're concentrating a whole bunch of odd things we've done into one chapter called Trigonometric Identities and Equations. Well, you've been using trigonometric equations. You haven't really solved many of them, but you've graphed a lot of them and you have looked at the properties of them. And we've actually used identities several times, but we're going to concentrate it all now in one chapter. So let's get started. We're going to deal with fundamental. When we say fundamental, they mean these are the most common sense ones that you really have to get down. The other identities that come up in this chapter, some of them are more obscure that you don't see that often, and some of them are actually you may never see. But these are the basics that we all need to have kind of like memorized. An identity is an equation that's satisfied by every value in the domain. It's basically another equation that represents something you've already were looking at. For instance, let's do the really basic. This should make some sense. We're doing those reciprocal relationships we had, and we've learned that cotangent was related to 1 over tangent. See, that's an equation that is true for all values of theta. We've learned that secant is 1 over cosine of theta. Cosecant was related to the sine, 1 over sine of theta. So those are 3 reciprocal identities. Okay, quotient means fractions. These were also fractions too, but they were special fractions. They were reciprocals. This would be another name to write tangent as a fraction was sine of theta over cosine theta. And another name to represent cotangent was basically, which is interesting, since tangent and cotangent are reciprocal identities, 1 over tangent, it's still reciprocal, but you're representing cotangent in terms of cosine and sine. The father of all Pythagorean identities, we have to memorize this one. Sine squared theta plus cosine squared theta was always equal to 1. Tangent squared theta plus 1. This is a harder one to memorize, but it's secant squared theta. I'm going to show you a trick in a second. One plus cotangent squared theta is secant. Whoop. Not writing. It is writing. Secant squared theta. How do I memorize those? Sometimes I really don't. But if you need to pull it out of your hat, this is the one you have to memorize. And if I know I'm dealing with secant squared and tangent squares, and I'm looking over here and I don't know which one is which, well, tangent squared plus 1 will always be secant squared, and cotangent, and I messed up on this one, I can tell right now. Let me fix this. 1 plus cotangent squared is not secant squared. I just noticed it. Sounded right. They always do sound right. It's close though. It's cosecant squared theta. And most of the time we don't use the whole word. We just do cosecant squared theta. And I was just going to show you, in case you want to double check your work or derive them, because these both are dealing with weird things like tangents and secant, tangent squares and secant squares and whatnot. Start with this basic. Forever and ever and ever, you need to know that sine squared plus cosine squared is equal to 1. Whether it's a or b, or sine squared a plus cosine squared a equals to 1. Sine squared of theta plus cosine squared theta is equal to 1. You can do two things to this thing. You could divide each term by one of these terms. I'll do a sine squared. Let's pretend you just don't know the identity, or you make a mistake and you're checking your identity. You find out that sine squared theta over sine squared theta is a 1 because they cancel out. So 1 plus, remember that quotient identity, cosine squared theta over sine squared theta is cotangent squared theta. Remember that reciprocal identity for cosecant was sine squared theta. Cosecant squared theta. So you have that one. So in case you forgot the identity, there's that one, starting from the original, okay? Let's put the original again. Sine squared theta plus cosine squared theta is always equal to 1. Now divide everything by a cosine squared theta. I'm just randomly choosing something to do because I don't remember my identities. Well, look what happened again. Cosine squared theta over cosine squared theta here is a 1. So that turns into sine squared theta plus cosine squared theta plus 1. Well, that's the quotient identity for tangent squared theta equals to, and this is the reciprocal of secant. So it's secant squared theta. So now, even if you forget these identities, you can always derive them really fast. All right, so let's pick up where we left off. More identities. Do you remember what we said about the sine of an angle versus the negative angle? Do you remember? Really quick. Just my reminder. Here is a 45-degree angle. 1 square root of 2. The sine of that angle is opposite over hypotenuse. 1 over the square root of 2, or square root of 2 over 2. If I do sine of the negative of that angle, that puts it down here. That's still a 1, but now that's a negative 1, and that's the square root of 2. The only thing that happens is the opposite over hypotenuse becomes a negative 1 over the square root of 2. So it's the same answer, except, let's see, the sine of a negative theta is negative sine of theta. The sine part was identical. It was just that the answer became negative. Using that same picture, we should be able to look at the rest of these if you forgot. Cosine. Cosine of this 45 was adjacent, which is a 1, over square root of 2. When I do the negative 45, the adjacent's the same. So this one turned into the cosine of a negative theta is the positive answer. Now, since tangent of a negative theta is the sine of a negative theta over the cosine of the negative theta. You can put both of those answers as a quotient, and you'll just get the negative tangent, which I've told you before that tangent operates a lot like sine. So that's why they both get negative. Now, when I'm doing the cosecant of a negative theta, it's just the reciprocal of that answer. 1 over sine of theta, which 1 over sine of theta is a cosecant. So really, we just pull out the negative of the cosecant to make it easy. I just don't want to think that hard, so I'm using those identities that we had. Secant was the reciprocal of cosine, and since cosine is already positive, since the cosine of a negative theta is already positive, then the reciprocal is still going to be positive. And since tangent is negative, the reciprocal will also be negative. So I'm just going to put negative cotangent theta. All right. Most people don't memorize all those things because you can actually derive it in a minute or so. Okay, let's move on. We also have the alternative forms of the fundamental identities. Well, all he's done here is he just moved stuff around. If sine squared theta plus cosine squared theta is 1, obviously you could sign it for sine squared theta. You could, solve it for sine squared theta and move the cosine squared theta to the other side. It's the same thing here. If we knew, well, here, that sine squared plus cosine squared is 1, you can move the sine squared over. That's all he's done. You just move this one over, or you move this one over. Right? And I'll turn from each of the... Okay, all he wanted you to do for that is, you have the reciprocal identities right up here. He said, write the alternative form. Okay, I think what he means is, take these reciprocal, and you can switch them around. In other words, cotangent. Those are the cotangent, secant, and cosecant. So let's do this. If cotangent of theta is 1 over tangent of theta, that means tangent of theta equals 1 over cotangent of theta. That's all he's saying to you. Because you can multiply both sides by tangent, then divide by cotangent. Or cross multiply and divide. You get back to the same thing. You get the cross multiply, you get tangent of theta times cotangent of theta equals to 1. And now I can divide both sides by cotangent of theta. And I get tangent of theta equals 1 over cotangent of theta. You can do the same thing with the other one. Switch those around. Instead of saying secant of theta is 1 over cosine, you can say cosine of theta is 1 over secant of theta. Instead of saying cosecant of theta is 1 over sine of theta, you can say sine of theta equals to 1 over cosecant of theta. Fun, fun, fun. Using the fundamental identities, if we've done these before, if we know that tangent of some theta is a negative 5/2, well, we know tangent's negative, so it can only happen with this. Remember, all students take calculus. So only tangent is positive in this quadrant. Tangent is positive in this quadrant, but tangent is not positive in these two quadrants. And so he helped you out. But he's telling you, We're going to stick it with quadrant 2, even though it could be quadrant 4. He wants the answer in quadrant 2. Find each value. First thing I have to do before I do any of these 3 problems is to draw my picture of the angle. He said quadrant 2. And theta, and I know it's a negative 5/3. If tangent of theta is a negative 5/3, and here's theta, and tangent stands for opposite over adjacent, then one of these have to have the negative. Well, obviously, the negative x. So now that I know this picture in quadrant 2, I can solve the secant of that angle. The secant of that angle is going to be, well, it's the reciprocal of cosine, and cosine is adjacent over hypotenuse, or you could say 1 over x over r, if you want to look at it that way. Either way, this is probably more complicated. Personally, what I would do is find cosine, and then take the reciprocal. Cosine of this angle is adjacent over the hypotenuse. Oops, I don't have the hypotenuse. So I need to use Pythagorean Theorem. This is a right triangle. 5 squared plus negative 3 squared equals to r squared, or the hypotenuse. 25 plus 9 is r squared. 34 is r squared. R, or the hypotenuse, is the square root of 34. I'm going to leave it like that. Okay, that's just the hypotenuse. Feel free to label it square root of 34. But I'm actually looking for the reciprocal of the cosine, because secant is the reciprocal of cosine. So the secant of this, take that answer of the cosine, what I just did, that cosine of theta is adjacent negative 3 over the square root of 34. But secant will be the reciprocal, which would be a negative square root of 34 over 3. Okay, now this triangle is very important because it's going to answer every question I have up here. I need to know the sine of theta. Let's see, let's go back to this triangle. Here's theta again. Sine is opposite over the hypotenuse. So that's going to be, opposite was 5 over the square root of 34. But we always rationalize. Multiply top and bottom by the square root of 34. Square root of 34, 5 square roots of 34 over, when you multiply the same thing together with square roots, out pops out the square root, so 34. Next, last one, the cotangent of a negative theta. Well, remember what we said about cotangent of a negative theta. We said that was equal to the opposite of the cotangent of theta. So I go back to my picture and realize, well, cotangent is the reciprocal of tangent. Well, I already knew the tangent was a 5 over a negative 3. And he gave it to me right here, too. So that should be really easy. Opposite of the reciprocal, negative 3 over 5, which turns that into a positive 3/5. So I flipped the tangent and change the sign. Was there anything? Oh, there was still more. When taking the square root, be sure to choose the sign based on the quadrant of theta. Because remember, all students take calculus, is where all the thetas have positive, or I should say not theta, the trig identity. It's where all the positive angles are at. Quadrant 1, 2, 3, and 4. The angles, not necessarily, I mean, it could be the angles are all positive everywhere, but that's not the point. The trig function, writing one trigonometric function in terms of another. He wants me to write cosine of x in terms of tangent. So I need to pull out an identity that typically has tangents and cosines in it. Probably going to pull out the secant squared one, because secant's related. Go back up and look at your notes. That we had tangent squared of x plus 1 was equal to secant squared x. Let's see if that's up there in my notes there. One of the Pythagorean identities. Wait, it's not there. It was on another page. You look for it. You can tell me if I'm right or wrong. I'm going to run with it, though, because I know tangents have cosines in them. Secants have cosines in them. So I might be able to turn this into sine squared x over cosine squared x plus 1 is 1 over cosine squared x. Well, actually, he wanted it in terms of tangents. So let me keep tangents in there. I'll do tangent squared x equals to secant squared x minus 1. And that gives me I'm going to keep tangent. I need cosine, so I'm going to do tangent squared x equals to 1 over cosine squared x minus 1. Take the tangent squared x, and I'm going to add the 1 equals to 1 over cosine squared x. Let me solve for cosine squared x. Let's do that reciprocal thing. Cosine will come up here, and tangent squared plus 1 will go down here. Cosine squared x will equal to 1 over tangent squared x plus 1. Square root both sides. Cosine of x is the square root of 1 over tangent squared x plus 1. That's a perfectly good answer, but, plus or minus. Whenever you do square root both sides, it's plus or minus. Probably he's going, if you look at that is cosine x equals plus or minus, that square root of 1 is a 1 over the square root of tangent squared x plus 1. But you're not allowed to leave a radical in the bottom, so I don't really care about it, but he's probably writing it as, if you multiply top and bottom by I'll just put it here in red here, multiply the top by tangent squared x plus 1 in the bottom times the square root of tangent squared x plus 1, then you end up getting cosine of x is plus or minus a square root of tangent squared x plus 1 all over. When you multiply these two radicals together, they cancel out, leaving just the tangent squared x plus 1. Personally, I I don't mind that answer, but a common rule is to always rationalize the denominator. That wasn't much. You're going to find out a lot of the stuff we do in this chapter. You go, why do I want to do that? Well, there is an occasion where you might need to put it in terms of cosine, but all right, right tangent squared of theta. No, not tangent. I wrote it wrong. Cosecant squared is cotangent squared theta over 1 minus cosecant squared theta. He wants it all in terms of sine and cosine. This is actually a very good trick. Whenever you're trying to solve identities, see if one thing is equal to another thing, turn everything to sines and cosines. So that would turn into 1 plus cosine squared theta over sine squared theta, all over 1 minus 1 over sine squared theta. So everything is changed into sines and cosines. But then he says simplify it. That's not fair. Okay, so this is just algebra. Treat this as a fraction 1 over 1, 1 over 1. It's going to be two fractions over each other, 1 over each other. So my advice to you is I just keep it simple. I'm going to do my famous multiply sine squared theta times the 1. That gives me sine squared theta. That's a plus sign. Take this 1, multiply it straight up. That gives me cosine squared theta all over the denominator multiplied together. So that's sine squared theta. All of this is over. Do the same trick again. Sine squared theta times 1 is sine squared theta. And that one was a minus 1 times 1. That's 1 times 1. 1 over the product of the denominator, sine squared theta. Take the top fraction. Sine squared theta plus 1 plus cosine squared theta is a 1 over sine squared theta over, and sine squared theta minus 1 was cosine squared theta. We talked about that earlier, over sine squared theta. Hey, look what's happening. This is turning into 1 over sine squared theta times the reciprocal of the bottom fraction, sine squared theta over cosine squared theta. The sine squareds cancel out. I'm left with 1 over cosine of theta. What was I supposed to do? Evaluate it in terms of sine and cosine and simplify. Well, that's pretty simplified. I'm gonna put that in my hat and save it. So what you pretty much did, you just proved what you proved right now. If they would have asked you to, 1 plus cotangent squared theta over 1 minus cosecant squared theta is cosine of theta. This could have been a problem. It could have said, prove this identity. Prove this identity. And I do all the same work that I just did, and voila, I got lucky and I get cosine of theta. I would get to this point here and I go, I proved it. I proved the identity. I proved the identity. But he wasn't really asking me to prove an identity. He was just saying, hey, go ahead and play this game. Turn everything in sines and cosines and see what happens, and then simplify. Normally, that's not how we do it. I normally say, hey, I already know the answer. Prove it. Show me all these steps that got me there. Another thing on this product, yep, okay. When working with trigonometric expressions and identities, be sure to write the argument. Yeah, don't do what I did a minute ago when I go sine squared plus cosine squared equals 1. Write sine squared theta plus cosine squared theta is 1. Write the argument. Is it correct to write sine squared theta? No, that's what I was just saying. That's not really right. I get lazy and I do that, but we shouldn't. And that's it for that lesson. Oh, lesson 2 is going to be a whole bunch of proving identities. I can't wait. Bye. There is a My Math Lab on 7.1. Okay, we're going to do 7.2, verifying trigonometric identities. I hinted at that at the end of 7.1. We're going to look at some strategies. We're going to then practice by working on one side. Then we'll practice by verifying both sides. But normally, we don't do both sides. We just do one side, and that verifies your identity. Hints for verifying. Make sure you know those fundamental ones that we did in lesson 1. You can't go very far if you don't know those fundamentals. Also, you got to know about the equivalent forms. You should recognize those. For instance, what jumps out at me right now with sine squared equals to 1 minus cosine squared is the idea of moving that cosine squared back over. So that should always look for those. Always look for this one if you can possibly find it. You can try to rewrite the more complicated side. Try to solve from that side. And that way, when you get done, the other side is simpler. Maybe you can make that complicated side turn into the simple side. It is sometimes helpful to express all trig identity functions, in equations in terms of sine and cosine. That's what we did on that last problem in lesson 1. On a very unique problems that are harder, sometimes you have to recognize the algebraic forms that were factored, like recognizing this as the x plus 1 squared, or the x plus 1y squared. And so if you recognize that, you could rewrite this piece into this if you could see it. Or if there's a minus, you could put that one's a minus. Also cubics, that hardly anybody ever remember that a difference of 2 cubes is always whatever sign is here, whether it's a sum of 2 cubes or the difference of cubes. The difference of 2 cubes, you have a minus x minus y. The sum of 2 cubes is x plus y. The insides look very similar, except for the sign switches. That was a minus, that became a plus. That was a plus, became a minus, but it's still the same. X squared, xy, y squared. This is hardly ever memorized. Most of the time we Google it and say, what were the sum and difference of 2 cubes? And everybody does that. The difference of 2 squares is supposed to be memorized. X plus y, x minus y. But you won't be seeing a lot of those. Those are pretty unique. Okay, showing you how that one algebra could be used. That's the same thing as an x squared plus 2x plus 1. X squared plus, if I substituted sine of x for x. So that you're supposed to sort of have memorized. It was right here. Well, not 1. Yeah, it is a 1. Where was that at? X squared plus 2x plus 1. Do you see it? It's this one right here, because 1 is y. 1 squared. So it's sine of x plus 1 all squared. Anyway, sum and difference of two trigonometric expressions. He's just doing some algebra. But he is taking 1 plus sine, 1 plus cosine. He's adding those two together. I'm going to do it different than him. He's probably going to have you find a common denominator. If you do common denominator, sine times cosine would be your denominator. This is missing the cosine. So you multiply top and bottom by the cosine. This one is missing the sine, so you multiply top and bottom by the sine of theta. And that's your least common denominator. When I said common denominator, least common denominator. So that turns into 1 times cosine is cosine over sine of theta cosine theta plus sine of theta over sine of theta cosine theta. Since the denominator is the same, it's cosine of theta plus sine of theta over the same denominator, sine of theta cosine theta. There's my trick. Cross multiply c times a plus c times b over c. Same answer. I do it right from here. Cosine times 1 is cosine of theta plus sine of theta all over the product. Sine of theta, cosine theta. To me, that's so much faster than the usual least common denominator. Remember that we said an identity that said tangent squared x plus 1 was secant squared x. The alternative of secant squared is 1 over cosine squared. So the more you remember that, the better. It's an identity. This is an identity because I can prove that this is this. I just did it. Secant squared is 1 over cosine squared. Think of an identity that relates tangent of x to cosine of x. In this case, because secant of x is 1 over cosine of x, which is another name for secant squared, equals tangent squared plus 1. What kind of function is the link? That was the reciprocal function. Lot to hold. When an expression contains 1 plus sine of x, I'm going to write it out. 1 plus sine of x. You can multiply this top and bottom by a 1 in the terms of 1 minus sine of x over 1 minus sine of x. And what happens is it turns the top into first times last, gives you a negative sine of x. That's the outer. The inner gives me a sine of x. And the first times first is a 1. The last times the last gives me a negative sine squared. Well, this was in disguise the negative sine of x plus sine of x canceled out. So you were only left with a negative sine squared over the 1 minus sine of x. Well, I still have the 1. And the 1 minus sine squared x could have been cosine squared x over 1 minus sine of x. It's just playing around with the identities that we know. This is just another way of writing 1 plus cosine of x. It's another way of rewriting 1 plus cosine of x. just manipulation. So you could do the exact same thing if you were starting with 1 minus sine of x, 1 plus cosine of x. You do the same thing. You just be multiplying by 1 plus sine of x over 1 plus sine of x, 1 minus cosine of x over 1 minus cosine of x, 1 plus cosine of x over 1 plus cosine of x. It just changes it. It's just a trick sometimes we do. All right. To avoid the temptation to use other equations to verify the means, one strategy is to, if you only, is to work on one side. Because you don't really want to change both sides. Because you're trying to prove the left is equal to the right or the right is equal to the left. So try to keep one of those sacred. For instance, I'm looking at this one, our first real example. I want to prove that this side is this side. So you need to pick a side. And so I'm going to pick the right side just because I'm a rebel. Actually, I'm picking the right side because there seems to be a lot of stuff I could do here. And sometimes you'll work for 10 minutes and you say nothing worked. You got to start over again. It happens. But I'm picking the right side because I could use distributive property. Now, mind you, when somebody tells you to prove this identity, they already know that it's true. They already know it's true. They're telling you it's true. So just prove it. So you just got to keep doing what you can do. Cosecant times cosine looks like that. Not very pretty. Plus cosecant times the sine is also not very pretty. And you just do whatever you see that could be done, like using your fundamental identities. I could change cosecant into 1 over sine of theta times the cosine of theta, 1 over sine of theta times sine of theta. You'll notice this gives me cosine of theta over sine of theta. This gives me, believe it or not, a 1 because the signs cancel. So what am I left with? Cosine over sine is the quotient identity for cotangent of theta plus 1. And I go, yay, I did it. I just proved it. That cotangent of theta plus 1. This is true. And I only manipulated one side. That's my advice to you. Stick with one side. Even for the problem he has us do with two sides, I don't really like doing two sides because then you end up making a mess. All right. So we have to decide on example 2, verifying this identity, working with one side. Sometimes I look at both sides and say, what could I do with either side? This side doesn't have a whole lot to work with. I'm going to choose this side. The reason I choose this side is because I can distribute the tangent squared into both of those. At least that's something to do. The most I could do on this side was to turn the denominator into cosine squared. That doesn't get very exciting. So tangent squared x times 1 is tangent squared x plus tangent squared x times cotangent squared x. I like to turn everything into sines and cosines sometimes, see what happens. Well, I don't really have to, because, well, I will, just to show you. Tangent squared x. What if I change this side to sine squared x over cosine squared x times cosine squared x over sine squared x? You should notice that these two are reciprocal identities. They cancel out to a 1. So now I'm left with tangent squared x plus 1. And that is the same thing as a secant squared x. We had that identity, which is the same as 1 over cosine squared x. And that's the same as, if you remember, sine squared x plus cosine squared x is 1. That's the same thing as 1 over 1 minus sine squared x, which is exactly what I was trying to prove. So I can, in Latin, you could put QED. That means I proved it. It is shown, it is displayed. Or I just put a check mark and say, I just proved it. Equals to 1 over 1 minus sine squared x. Third example. Okay, which side looks uglier? They both look ugly to me. I will pick the left side. What I'm going to do is break this up into two different fractions, because I got two different things here, so this might be in the right direction. Tangent of t over sine of t cosine of t minus cosine of t over the same denominator, just to see what happens. And maybe nothing's jumping out at you at the moment. So at this point, if you don't see anything else, change everything to sines and cosines. Just see what happens. Sine of t over cosine of t over, this is the tangent. That's all tangent right here. Sine of t times cosine of t minus cosine of t is already in cosine. Oh, it's cotangent, sorry. That's cosine of t over sine of t all over this denominator. Sine of t cosine of t. And you always treat your bottom as like another fraction. So when I multiply this fraction here by the reciprocal of this fraction, it looks like this. Sine of t over cosine of t times the reciprocal of this 1 over sine of t cosine of t minus cosine. It was probably cosine anyway, wasn't it? It was a cotangent, so it should have been a cosine. Yeah, cosine of t over sine of t times the reciprocal 1 over sine of t cosine of t. And then this sign cancels out that sign. I'm left with 1 over cosine of t times another cosine of t. That's 1 over cosine squared t. And then here, this cosine minus 1 over sine squared t. Am I getting closer to the... yeah, look at that. Let me go up here. 1 over cosine squared t is the same thing as a secant squared t. And 1 over sine squared is the same as a cosecant squared t. And I have just proved it because that's the same thing. Same thing. Sometimes they get really hard. And sometimes you got to do it more than once. Verify this one. They both look equally ugly. So what I'm going to do is I'm going to start with my cosine. I don't know which way is better. You just got to pick one. Pick something. I can multiply top and bottom by, we've had this in the other rule, other hint, 1 plus sine of t, 1 plus sine of t. Now, mind you, I'm just making something up. What else can I do? I mean, all I had was a 1 minus sine in the bottom, so I multiplied by 1 plus sine, which is this is just equal, all of this is just equal to 1, so it was legal. Okay. That turns into cosine. I'll distribute this. Cosine of x plus why did I say x? They're all x's. I don't know why I put a t here. Cosine of x plus cosine of x sine of x all over 1 minus sine squared x. We talked about this already. 1 times 1 is 1, minus sine times sine is a minus sine squared, but the 1 plus and the 1 minus, that goes away. Does that help me at all? Let's see. Sometimes you got to go back up and realize, well, what am I looking for? Well, I already have the denominator done. I already have the denominator done. Interesting. I just thought of something. I already have the denominator done. 1 minus sine squared is cosine squared. And if I would not have distributed the top, so I'm going to undo my distributing and go cosine of x times 1 plus sine of x. I undid it because I see something. If I cancel one cosine here and I don't know why I keep doing that, and then one cosine here, I'm left with 1 plus sine of x over cosine of x, which is, that's what I wanted. So I just proved it. It's the same as the right side. QED, or a big fat check mark, So I'm just rolling with the flow. I didn't always know what would work, but you just keep trying. Let's try another. All right. What are we doing now? We're going to work with both sides. That could be fun. And we're not doing both sides at the same time. He just wants to try to see if we can do it from both sides. And I can't guarantee I can, but we'll try. Let's see. I'll start with I'll keep the left all the way down, and then I'll see if I can manipulate the right side to turn into the left. And I'm not even positive I can do it. I recognize the algebra in this. If I let x equals to sine of a, then this is really 1 plus 2x plus x squared. And when you factor that, it's x plus 1 times x plus 1, or x plus 1 squared. So that top, just by looking at it, I'm going to call that a 1 plus sine of a squared over cosine squared a. And cosine squared a is the same thing as 1 minus sine. So I have 1 plus sine of a times 1 plus sine of a over 1 minus sine squared a. But I don't know how that's going to help me get a secant and a tangent and a secant and a tangent. So I look at that and I say, well, let's see. Look at trying to create. Not very helpful. And that's a difference of two squares. So I have 1 plus sine of a, 1 plus sine of a over 1 plus sine of a times 1 minus sine of a. That's a difference of two squares. And well, that causes those two to go away. So I'm now left with 1 plus sine of a over 1 minus sine of a. Now, I can't do anything else. So I'm going to pause right now on that and just say, well, let me attack the other side now. Let me start with the secant of a plus tangent of A over secant of A minus tangent of A. And what I'm going to do is try to keep this moving down, and it's all, I'm leaving this here, okay? So what can I do with this? The only thing I think I can do is maybe, remember that trick we did about multiply top and bottom by the same thing? But I'll change the sign of the bottom to be secant plus. So I'll go secant A plus tangent of A over secant of A plus tangent of A. And the bottom, the top becomes that's a secant of A plus tangent of A squared. Bottom becomes, it's a plus and minus, so it just becomes secant squared A minus tangent squared A. See, is that getting close to that over there? No. That didn't help at all. And sometimes you get to a point where anything I do is going to take me back to the beginning. So sometimes you got to start all over and say, well, that didn't really help. And so I remember in the day going through 10 pages of paper. What else could I do? Let's see. Trying to look at the original again. Okay, I'm seeing a cosine in the bottom. And when I multiplied by the plus plus, it didn't really help. Let me multiply by a cosine of A, just because it is at least one of those in the bottom. If I use, okay, there's a relationship between both of those. Watch. Sometimes the light bulb clicks. Sometimes it doesn't. You're going to see this. I see it. I can see ahead. Of course, I'm old, and I've done stuff before. But I still had to start over. There's no crime in that. See, what happens is you realize that if I break that cosine up next to the 1 over cosine, whoop, that's cheating. I didn't use the argument. Cosine of alpha times 1 over cosine of alpha using the reciprocal identity plus the cosine of alpha, and look at here, sine of alpha over cosine of alpha using the quotient identity for this, using the reciprocal for this. Something's happening. This bottom cosine of alpha times 1 over cosine of alpha minus cosine of, I've lost the alpha there, alpha times sine over cosine of alpha. Again, quotient identity, reciprocal identity. And what happens here is this two cosines cancel out. That cosine cancels that out. That cosine cancels that out. That cosine cancels that out. What am I left with? I'm left with 1 plus sine of theta, sine of alpha over 1 minus sine of alpha. That sounds familiar. 1 plus sine, yes, look at that. They both took me to the same place. So I used both sides and I worked until I got something I could not go any farther with. Then I went to the other side, kept working until I got to something that I couldn't go any farther with. And it just happens to be the same thing. QED. I'm pretty proud of that one. I had no clue how to do that one. Explain how to work both sides. Well, working with both sides, as long as you don't work on both sides at the same time, that you could get this one down to a simpler, you get both sides. You could get both sides to the same simpler expression. Yeah, I'm proud of that. And am I going to work on this one? Applying Pythagorean identity to electronics. Woohoo. Tuners and radios select a radio station by adjusting the frequency. A tuner may contain an indicator L and a capacitor, inductor, it's not indicator, induction. It's an inductor. Electronics has inductors and capacitors. Inductor L and a capacitor C, as illustrated in the figure. Okay, so inductor L, capacitor C, they're in this. This is a circuit diagram. The energy is stored in the inductor. Look at that. Looks like a coil. So it's like a battery. So it's storing here in the inductor. And the energy stored in the capacitor is this equation. So you've got another small storage over here. Okay? So you have two equations. Both of them have a constant K. So we don't really know what K is, and they both have an F and a T, an F and a T, where F is the frequency of the radio station and K is the constant. The total energy, E, in the circuit is given by, well, obviously, if you add the inductor storage and the capacitor storage, you have the total energy in that circuit. Show that E is a constant function. If E is a constant function, then E has to be equal to some number. It could be any number. And let's see, I don't know. Let's just write out the equations they gave me. E of t is equal to a k sine squared of 2 pi f t. 2 pi frequency, there's my variable t. It's like saying x. 2 pi ft. And plus, the capacitor is a k cosine squared of what? 2 pi f, and here's my variable, t. So all of this just stands for some number times your variable. Some number times your variable. It could be 2t, 5t, who knows? But they're the same number. What do I know about the k? It's in both, so I can factor out k and leave sine squared of some number plus, with a t in there, plus cosine squared of some number with a t in there. The point I want you to see is that, k is on the outside. This is sine squared of something plus cosine squared of something. No matter what that number is, no matter that it's a 2 pi f, 2 pi f, it doesn't matter. It's still equal to 1. K times 1 is k. There's your constant. Okay. And that's it for lesson 2. Stay tuned. Just leave it at that. Bye. Now you got 2 My Math Labs. For lesson 3, where we learn something very useful in the future, sum and difference identities. But for now,